Hello, accelerated biology students. Mr. Adair here, giving a lecture on the properties of water. So today is Wednesday, actually, I'm recording this, but tomorrow will be Thursday, October 1st. Hopefully, you use today to get caught up on some of your work. I'd like to go a little bit, I'd like to talk a little bit about the properties of water. Now, in class, we would normally do a bunch of labs regarding this topic, but obviously, we're not going to be able to do that exactly. So, I do want to present the information, and I'll share the Google slide as well. All right. So, in order to really understand about life on Earth, because biology is the study of life, we do need to know a little bit more about water. Most of our bodies are made up of water, and water is really one of the main reasons life can exist on Earth. Before we totally can get into understanding about the water molecule, as you can see here, on the left-hand side, you have a H2O, two hydrogen atoms covalently bonded to an oxygen atom. The hydrogen atoms have a positive charge, and the oxygen atom has a negative charge. This is important. The H2O molecule on the left is a very solid, secure molecule. The covalent bonds make it extremely strong. So covalent bonding is kind of like handcuffs together. It's very strong. However, when we have several H2O molecules bonded together, which actually kind of forms water, if you can imagine a glass of water, it's millions and millions, if not trillions, of tiny H2O molecules all hydrogen bonded together. A hydrogen bond is more like a magnet. Positive and negative attract each other. And this kind of makes sense when you think about it. A H2O molecule won't really break apart easily at all. But H2O molecules that are bonded together, like in a glass of water, can break apart from one another, meaning one H2O can break apart from another H2O. If you've ever boiled a pot of water, you excite all those H2O molecules and they actually break apart from each other and change from the liquid state to the gas state. Okay? All right, some vocabulary that you need to know. Solute is the substance dissolved in a solvent to form a solution. And I'll explain more about that in a moment. And solvent is the fluid that dissolves the solute. Water is the solvent of life, meaning many, many things can dissolve in it. So, for example, if you've ever made Kool-Aid or lemonade, like with a powder, or iced tea with a powder, the powder is considered the solute. The solvent is the water. Um, Also, sugar would be solute. Salt would be the solute, whereas the thing that does the dissolving is the solvent. And I found this old video.
I get hot and thirsty riding a skateboard. Me too. This is a job for Kool-Aid. Hey, Kool-Aid!
Yeah, Kool-Aid's here, bringing you fun. Kool-Aid's got thirst on the run. Get a big, wide, happy ear.
And there's Kool-Aid style. Tastes great. Our friend's cool. Our friend's Kool-Aid. Kool-Aid brand soft drink mix.
Oh, yeah.
Well, I just had to add that in there because they don't make commercials like they used to, right? All right, a couple more vocab words that you need to know. Cohesion versus adhesion. Now, cohesion is the property for water to attract to one another. So, the water molecules that attract to each other due to hydrogen bonding, we consider that they're cohesive to one another. Adhesion is when water is attracted to other materials besides itself. So think about like an adhesive band-aid. The band-aid is attached to your skin if you get a cut. Adhesion is where the water is attracted to a different material. If you have a test tube and you pour water in it, if you look at the image on the right, if you look very, very closely, it's going to have like kind of a sink, a divot in it because of adhesion. Some of that water molecules slightly being attracted to the atoms of the glass test tube. In class, we would do a thing. How many drops of water can fit on a penny? If you if you notice and look at this image, you can see the water forming kind of like a dome. And it's really kind of staying together because of the properties of cohesion. All right, another property of water that we need to look at is surface tension, which is the result of cohesion. The water molecules bonding to each other, forming a layer that has a little bit of strength. It can hold up some very lightweight things. Like, for example, in that upper right picture, and you can try this at home. You should try this at home. If you can find a paper clip, fill up a glass of water and let the water just be on the very top of the brim, and then very, very, very carefully try to float the paper clip on the water. If you can do this, it's a good example of surface tension. It does take some practice. And some insects master surface tension. They live on top of the water. They're so lightweight, they can basically walk on water. And this will be a good segue into the miracle lizard. So as you notice from that video, there's enough surface tension and the lizard is so lightweight and running fast enough it can almost use that surface tension of the water as an opportunity to run across it. Okay, this next video is a little bit longer. It's about 8 minutes. We're just going to watch it and it's going to go over some of the same things we talked about.
Hi, it's Mr. Anderson, and in this video I'm going to talk about water, a polar molecule. What does it mean to be polar? It means that you have a charge. The electrons are shared unequally, and as a result of that, water has these amazing behaviors that allow us to survive on our planet. And so let's start by looking at one water molecule. It's made up of one oxygen atom and two hydrogen atoms, and what you should know is that oxygen is highly electronegative. What does that mean? It's going to pull electrons towards it, and if we were to look at those levels here on the periodic table, aside from fluorine, it's going to be the highest one there. And so why is that? Well, if we go across on the periodic table, we're seeing an increase in electronegativity. Why is that? We're increasing the number of protons in the nucleus. Therefore, there's more positive charge on the inside, so it's pulling those electrons towards it. And you might think, well, then as we go down on the periodic table, why doesn't it increase there? Well, as we go down, we're filling in more levels of electrons. And so these electron levels that are filled are shielding that pull of the protons on the inside. And therefore, we have to go up on a periodic table to get electronegativity increases. And so oxygen's really high. It's pulling the electrons of hydrogen closer to it. And so what you get is a partial positive and a partial negative charge. In other words, the oxygen's always going to be negative, and then the hydrogen's always going to be positive. And so you can think of it almost like a magnet. There are going to be poles or two sides to it. And just like magnetic fields move out around the magnet, you can imagine these imaginary fields around the water molecule as well. And so on the top, where the hydrogen is, we're going to have positive charges, and then on the bottom, we're going to have negative charges. And so imagine trying to put a bunch of magnets together like this and just holding them there. Now you know that those similar poles are going to repel each other, and so if you were eventually to let go, it would quickly shift to a shape like this, where south meets north and north meets south. The same thing would occur with water. If we put water molecules like this, all of these negative charges of the oxygen molecules are going to repel each other, so it'll quickly orient itself like this. And so water will always be oriented so the positive of the hydrogen and the negative of the oxygen are attracted to each other. And so what do we call that attraction between these? We call those simple hydrogen bonds. And so the hydrogen bond would be represented with these dotted lines. It's an attraction between the positive hydrogen and the negative oxygen. Sometimes we'll see hydrogen bonding with nitrogen as well. Now, what are some of the properties that we get as a result of this polarity? The biggest one that you can see right away is cohesion. What does that mean? If you think of this as one water molecule and this as another water molecule, then the positive here is attracted to the negative here. So if I pull this in this direction, this is going to go with it. And so it's holding all of those water molecules together. And so the surface tension in this water right here is caused by all the hydrogen bonds in the water molecules. Where this doesn't occur on our planet, but in space or in orbit around our planet, this is a big globule of water, and it's just floating there. What's holding it together is going to be the cohesion, or the hydrogen bonds of those water molecules. What's another property? We have capillary action. What does capillary action mean? Well, if we were to look in this tube, it's just sitting in water, there's starting to be adhesion to the sides of the tube. Now, how is adhesion different from cohesion? Adhesion is when water is sticking to another surface, anything that has a charge, and so you can see it's kind of creeping up on the side. What's pulling the other water molecules along with it? That's going to be cohesion. But you can see as we decrease the size of that tube, it goes higher, and as we make it smaller, it goes higher yet. And in fact, if we make it microscopically small, so like the xylem, which are these tiny tubes in a tree, that's how water is moving all the way up a tree. There's evaporation of water up at the top, and then there's this connection of water all the way up these tubes to the surface, and so it's moving all that water through a tree. What's pulling it up? It's going to be the driving of that energy from the sun, but it's the connection of all those water molecules. It also accounts for the high specific heat of water. What does that mean? It's really hard to change the temperature of water. And the reason why is to change the temperature, you have to pull those molecules apart. And if you want to evaporate it, you really have to free up one of those water molecules. And so I live in Bozeman, and so Bozeman looks just like this, surrounded by beautiful mountains, but we're at about the same latitude as Seattle. Now, Seattle, instead of being surrounded by mountains, is surrounded by water. And since that water has this high specific heat, what it does is it moderates their temperature. So this is the average high temperature in Bozeman and in Seattle. And you can see Bozeman is this yellow line. In January, it's going to be in the 30s or high 30s. And then in the summer, it's going to be in the upper 80s, pushing 90. But if we were to look at Seattle, its temperature is really not going to vary that much. And it's rare that they have really icy roads and a lot of snow. And it's also rare that they're going to have 100-degree temperatures in the summer. Why is that? It's the high specific heat of the water that's surrounding Seattle. So for example, in the summer when it gets really hot outside, a lot of that energy is going into the water itself. It's absorbing a lot of that energy. And as it does that, it's kind of moderating the temperature. It's a good reason why you're filled with water as well. If you weren't, our temperature would change radically over the course of even a day. Another property is that ice floats. And you might think, well, that's obvious. But with most matter, with most molecules, when you cool them down, they become more dense and they would therefore sink. But water doesn't do that, and that has to do with these hydrogen bonds in here as well. So as it cools down, it's forming this beautiful three-dimensional matrix, which allows it to actually decrease density. Why is that important? Well, if it didn't do that, then ice would settle at the bottom of the oceans and we would quickly be a frozen planet. Another important thing about water being polar is that it's a good solvent. And so this is a PHET simulation. What I'm doing is adding a little bit of sodium chloride or salt to water. And you'll notice what happens, that when we add that to water, it breaks apart into its ions. And so the sodium and chloride ions are actually being ushered away by the water molecules. So if we get rid of the water, it goes right back to that ionic salt. So if we zoom in a little bit closer, what's going on? Well, let me kind of pause it right here. So what do we have? We have this chloride ion, which is going to have a negative charge, and it's going to be surrounded by the positive parts of the hydrogen. Likewise, we have this sodium ion, and so it's a positive charge. You can see that it's being surrounded by the negative charges of the oxygen molecules. And so as a result, that allows us to dissolve material really, really quickly. And as we move materials around in our body, it's important that we're made of water, a very good solvent. And there's this saying that like dissolves like. And so let's say we have water, and then we throw a little sugar, a disaccharide next to that. Well, what do you see? A bunch of oxygen, a bunch of hydrogen, and so that's going to be polar as well. And so we're going to have areas that are negative, and so the positive hydrogen is going to connect to that in areas that are positive, and then the negative oxygen is going to bond to that. And so what happens when we add sugar to water? It's going to dissolve quickly. And the reason why is that like is dissolving like. Now if we were to look at another molecule, this is a triglyceride.